What I'm going to have a look at today is something I've been struggling with, and we've been struggling with trying to show it on the video. So we'll have a go and see what we can do. We're going to have a look at the topic of freefall and have a look and see what we can do with that. So let's have a go. I've got here a Lego freefall machine. It's not quite there, I failed. And we've got here a Lego little Mindstorms EV3 box, and we've constructed a dropper and a catcher, and what we've got is a ball bearing, and we're going to drop this exactly 50 centimeters from the top to the bottom. We've got a little button to press, and if we press it, we can drop it. Let's have a look and see what we need to do to play with this and what it can do. So our starting idea is that we've got some sort of track here which is 50 centimeters, and at the top here I've got a system holding a ball bearing. This will swing out of the way, and at that point we start the timer. The ball then falls down and hits a stop switch, and then we're going to get some sort of time displayed so that we can work out how long it takes for this to fall down. Now, it's not particularly easy to do this. The standard way of trying to do this is much more sort of easy to do in the lab and quite difficult to do on the video. In the lab, what we would do is simply take here a black surface, and with this we can put in a little ruler, and what we do is we drop the ball, and what we've got here is my camera and flash gun, and the flash gun here is a strobe flash gun. And so we open up the aperture, and what we do is we get the readings of the ball falling, and what we see when the ball falls, it gets gradually larger and larger because we can then work out the acceleration due to gravity. Not so easy to try and do that and achieve it, although we can get some sort of results doing that, and doing those sort of results I've got something akin to this, and you can just about see here we've got the ball falling vertically, and you can see it's just about accelerating, and then we've got to the other side here some other ones. This is the ball fired instead horizontally, and we get a different trajectory, yet these balls line up, and the distance it's travelled down, they are the same. So the vertical distance is the same, but this one's also got a horizontal trajectory. As I said, that one's not particularly easy to see because of all types of problems with strobes. We can also look at this in a different way, and the different way we can try and look at this one is we're trying to capture the video, and I've got the video captured, and we'll look at this frame by frame. So if I just have a look at this one, we can see that we've got here our catcher, and when I've released it, there's the ball, one frame on, the ball's fallen, one more frame, and another one, and so on. So we can capture this. This is with a program called Tracker, which is very good for trying to do some things, but not wonderfully with this. So it sort of does cause a few problems trying to do it this way. So let's see what we can go and have a look at and see if we can do some measurements of freefall and see what happens. So let's go over to the setup and see what we've got. Right, so let's see. We've got at the top here, and I'll just zoom in a little bit. We've got the launcher, and this simply we put in a ball bearing, and we found that this mass, which is about just over 1 centimetre across, seems to work quite well. And we have a switch we release, and as I release, watch what happens. So it comes out, opens up, and the ball falls, and we got a time for that one. So I'm just going to load it up again. Down here we've got a very simple little switch. I press the switch and this motor at the top opens, and at the same time the timer starts, and then down the bottom here I have a little plunger, and you can see the little white handle moving as I push it down, and that stops the timer. And we have a peculiar piece of Lego in there, which is a plastic piece of, not rather than plastic, it's a rubber piece of Lego to try and absorb the impact. Okay, all this is powered by an EV3. This is a simple Linux powered Lego brick, and rather than having all the equipment, we can set this up. So let's use one of these things to save a lot of time and effort, and we're going to do this experiment a few times and record our results. So let's zoom out a bit and we'll see what we're doing. A little bit more, I think. There we are, brilliant. So they can see what's going on. Right, so let's start. First impact, and that is 0.34 of a second. Let's do it again. Happy face on my little thing. 0.342. I have struggled trying to get it out. We've got a little plunger, and I can pull it out with a little plunger quite easily. Let's load this up again. Right, we're ready to go. And that is 0.343. Amazingly, that caught on the top. We're going to do 10 readings. That one didn't work terribly well, because that hit the plastic. I got a miserable face for that one. Let's try again. Good shot.
Yeah, I am. But I'm about to leave.
0.343. Not 0.346. Good shot on that one. 0.340. Considering the system setup doesn't change, it's not moving very much at all, we do get a fair bit of misses, like that one where it jumped out. 0.345. Not 0.346. We've done 2, 3, that's 8. We'll do a couple more. Not 0.342, and our last run 0.347. So we've managed to get a set of 10 values. Let's go and have a look at them. So we're not wildly inconsistent here. We are the difference here of 7/100ths of a second, which is reasonable considering, I suppose, it's a piece of Lego setting it all up and doing it with Lego here. So we're going to try and first of all work out an average of these numbers, and if I just try and call this up. I've got my calculator and I'm going to cheat here, so we're just going to have 2 plus 3 plus 3 plus 6 plus 5 plus 6 plus 2 plus 7 is going to give me 34. Divide that by 10 is going to give me 3.4. So I only added up the last column, all the others being the same, so 0.34, and then it suggests that 34 is our average here, and so we can either use that number or we can take our best number there. Right, so we have now managed to work out our time taken, and that's measured in seconds. So what can we do now? Well, let's start with a little formula, and we're going to use something like our suvat. I know my distance. This is 0.5 of a meter. I know my initial velocity is 0. I have absolutely no idea what my final velocity is. Acceleration, well, this is what we're here to calculate, and I've got my time, which is 0.343. We've got a distance and we've got a time, but I want to work out the acceleration, and what would seem to be best is use a formula like S equals ut plus a half at squared. Ut we know is 0, so we've got here just S equals a half at squared. Now we could do various things here to try and work out what it is, but we're just going to use a simple calculation here. So if I want to rearrange this, we've got 2s divided by t squared is going to equal a. So let's just put in our values. 2 times half a meter is actually going to give me 1 meter, so it's going to be 1 over 0.343 squared is going to give me a. Let's just work this out on the calculator. So I've got here 1 divided by 0.343 all squared, and that's going to give me my acceleration due to gravity, which is 8.499 meters per second squared. It's a bit off from what gravity should be. Now, why can that be? Well, it could be that I've got a gravitational anomaly around my sort of work area. It appears to be very true, because when I have students here trying to do this, we get quite a lot of gravitational anomalies, and we've had gravity reported from being in the minus value, which is anti-gravity, which I haven't discovered yet, to having this somewhat larger than the force on Jupiter. So there is quite a gravitational anomaly just around these few feet. Having taken that into account, what's the most likely cause for the problem? Well, did I get the measurement exactly right? And the answer is no. I think it's about 1 millimeter out. So I can live with that. How about the timing? Well, one of the problems that we've got with the timing is that we've got this from me pressing the button here to the time where it's actually going to release, and that does seem to be consistent, but it does vary. And I'm pleased to tell you that pressing the button here is now not having any effect. I'm going to stop the program and restart it. No, I won't. I've decided that I've managed to lock it all up. Yep, takes skill, but I have actually managed to crash the program. Right, I'll walk away and leave that then. That will give us a little bit of grief trying to work out how we're going to reset that. My son will now have a go at trying to do that for us. So a minor change in that number is going to make a little bit of difference. If we'd had a time like our maximum time, which is 347, then if I just go in and edit that, then you'll see that here we get quite a smaller number. If I'd gone in and put in the smallest number that we've managed to get here, then it's not going to vary too much. We're still within the eights. The extra points not making a significant difference on this. If I'm looking at this number, I'm getting 0.865 if I did that one. So it's not making that much of a significant difference. So we've got the freefall here working. Now, can we reverse this and see what the time should be? Yeah. We can do that one quite happily. And that we're just going to do with changing those numbers round here so we can work out what it's going to be. Let's try this out. So here I've got again my formula, S equals a half a t squared. We've got a this time, and we're going to work out what t is going to be. So this is going to be 2s divided by a is going to equal t squared. So we're going to need to square root that to get what the time should be. So 2 times 0.5 is again 1. 1 here divided by 9.8, and we'll square root it. I'm only going to go to 9.8. Considering we're that ineffective here, we'll use those numbers. So I've got the square root of 1 over 9.8, and that gives us a time which should be about 0.319, so 0.32 of a second. So that's the timing that we should have expected from this, but trying it out, it's working out rather different. Now, something that shouldn't make a lot of difference to this, but does, is if we use a different size ball bearing. And what we'll try and do is see if we can do this. Now we've got this now ready set up here, and it should work. And it does bounce out, and that may make a difference, and that's 0.329 at this time. So we're getting a bit of difference, 0.329. So I don't know what the difference was there. So I better record some of these. 0.329. Let's try it again. Ball is bouncing out, which is a little bit of a worry. 0.327. So again, even faster. What I've worked out is I've lost a little plunger to pick it up with. Try again. 0.327. Nought 0.327. These are in fact the values that we got when we practiced this earlier. Nought 0.330. I've lost my plunger. Yeah, doing well. It won't be far. The reason I was using the plunger is because it's so difficult to get this ball bearing out of the bottom. One more time. 0.325. Let's try it with a smaller ball bearing. So I've now got a much smaller ball bearing than I had. We've got the two sizes. This one then is about a quarter of the mass. And a time of 0.312. Now the difference in timing is due to the size but not the mass of the ball bearing. That one unfortunately missed completely. This is why we didn't use this small ball bearing. We'll just get the top set up again, so hopefully it'll fall in the right place. There it did. This is 0.312. And we'll just do one more. Hopefully we'll do one more where it can hit the target. Nought 0.311. Nought 0.332. We got, with the other ball bearing numbers, a little bit more in that range. And if I try the calculations to work out what they are, so let's see what we've got. We've got here 329, 327, 2727, 330, 325. We'll average that out at 327. And if we use that value in our equation, which is going to be basically 1 over 0.327 all squared, then we're going to get 1 over 0.327 all squared. We're going to get a value here of about 9.35 meters per second squared. But that doesn't answer the difference about the two ball bearings. The two ball bearings are different sizes and they give different values. Now why? Well, it's not to do with the mass of the ball. That makes no difference in this whatsoever, but it does make a lot of difference to the timing. The timing here is geared to this ball, and we've got our piece of Lego that's holding the ball, and it takes a finite amount of time for this to come out, and when it reaches a certain point, this ball is able to fall down. Now if this ball is smaller, then it can fall down slightly earlier, and that can make enough difference in the timing to make quite a difference in what we're looking at. So this small ball makes a difference here in the readings, so we have to be careful of this. So these were the values I was expecting. These are the values that we got first time. These were all slower than I was expecting. These are of the right sort of time. And I'm expecting to get a value of 0.32, and unreasonably happy with those values getting sort of an answer here. So we've got this idea of gravity by freefall. We can use other equipment like this program, which is Tracker, and we can use this along with a ruler, and I can just drop the ball and take pictures with a high-speed phone, as long as we can manage to capture and know how long that is. The basic problem with some of the cameras is they don't have an absolutely consistent shutter speed. They should do, but it varies very slightly. If we can do that with a strobe, we can get it much more accurate. So the strobe is definitely the better way to go, and that does still cause a few issues with various sort of problems trying to sort of see it, that we get a picture like this, and that one I'm going to have to zoom in to show you. That we can get the dots, and if I put the ruler with this, then it is possible to simply work out what the time was, because that's the same time each time, and the distance fallen, and so we can get this by, we can work out an accrued time, and a distance taken. So here we're going to have time, here we're going to have distance, and we find we've got a nice, hopefully straight line here plotting distance against time squared. and that will enable us to work out the acceleration. Typically when we do this, our acceleration is negative. Because it's simply falling to the ground. So we normally set our answer G to about 9.8 meters per second squared for when we're doing this. And our experiment here, the second time, is within the realms of this system. 9.3, we should have had 9.8. Perhaps if we try this again a few more times we can get this working a little bit better, but for now that's about the best I can try and do. So there's Gravity by Freefall. Either looking at it through something like a strobe, which is quite a good way of doing it. Many cameras now have a stroboscopic flash gun. We can use a program called Tracker, which is a physics program, which is free. Go and have a look for Tracker, and you can download that one quite happily for free. Typically I don't have the URL enabled for me, no. So Tracker's quite a good program. Taking the strobe, taking the photographs in Freefall, or just doing a video even and trying to track it. The problem with that is when we try and do the tracker, that it causes a little bit of grief, because if we go back and have a look at this footage, then we can see that this ball when it falls, this is not a really accurate ball. This is quite blurred, and as we go down to the next one it gradually gets more blurred. Here we got this distance from when the shutter opened until the point where the shutter closed, and you'd have to take an average of that. The strobe, on the other hand, is taking a more accurate picture to try and work this out. So however you do it, you can manage to work out gravity, whether you're going to use special machinery, whether you're going to get what I've got here, which is just my Lego contraption, and it works quite well, but not probably as well as a dedicated piece of machinery is. But anyway, you can still work out. So there we are, Gravity by Freefall. If you found this video helpful, then please remember to subscribe. So, at focus well up there, and I will see you next time on A-Level Physics by Physics, topic by topic. See you then. Bye bye.